Hi everyone, I am Anubhav and today I'll be talking about a systematization study on secure randomized caches. So we'll start with a little bit of background, wherein we see that a CPU usually talks to a random access memory or the main memory to get all of its data. And the cache sits somewhere in the middle of the CPU and the RAM, wherein it is smaller than a typical RAM, but much faster than it. And it helps hide the memory access latency of the large memory access latency of the RAM, and the CPU will basically be able to get faster results because of the caches. And the caches are typically divided into three levels in modern processors. The level 1 and level 2 caches are typically private to the core. And the last level cache or the level 3 cache is usually shared among all processors. This sharing is something that can lead to various types of last level cache attacks or LC attacks. And we'll discuss two classes here. The first being occupancy-based attacks. So in an occupancy-based attack, consider the setup where a spy and a victim process run on two different cores, and the level 11, level 2 caches are obviously private to the cores, and they share the last level cache. So this setup is basically from the website fingerprinting attack, and the spy will basically access a cache size buffer repeatedly while the victim is running its sensitive process. And the more the number of accesses that the spy is able to make to the same buffer, the less you can infer that the less is the victim LLC occupancy. And this basically leaks information about the victim LLC occupancy and can leak some sort of sensitive information about the process it's running. Similarly, we have conflict-based attacks. The setup remains similar. This is from the prime plus probe attack. But in this case, the attacker will now use something called an eviction set. So herein A and B form an eviction set, which basically means that they can fully occupy one particular set in the cache. And the victim will now run its own secret dependent process. And let's say it accesses V, which evicts the entry B in the cache. And now when the spy tries to probe for its entries, it sees a miss for B, which basically is due to the high timing differences between a hit and a miss. And that will basically help it infer that the victim accessed an entry in the set. So there have been multiple popular randomized cache designs which have attempted to mitigate these LLC attacks. So the first being Caesar, which basically uses randomization using a block cipher, and it tries to remap or rekey this block cipher every now and then to make sure that the attacker cannot reverse engineer the mapping. But this was broken quickly, and then we had Caesar and Scattercache, which are similar designs, wherein they use skews on top of the randomization and remapping to make sure that the address to set mapping is even more difficult to decipher for the spy. And then finally, we have really complex designs such as Mirage and Maya, which actually decouple the tag and data store, wherein they'll have a set-associative lookup in the tag store, and then a pointer-based lookup from the tag to the data store. And the data store also uses global random eviction. They also use external valid tags on top of the existing tag store to provide better security and to make sure they don't get any set-associative evictions or evictions from the same set in the cache, which helps leak information. Right. So this is an overview of the talk. So we'll basically talk about how we systematize the design space for secure randomized caches, and we basically identify a bunch of key security knobs in these designs. We also perform a security analysis of each of these knobs against conflict-based attacks. And finally, we study which combinations of these knobs work. So we'll also analyze these knobs against occupancy-based attacks at the end and compare them with partitioning-based designs. Right. So we have the security knobs as follows. So we have five key knobs, as in skewing, high associativity, external valid tags, remapping, and as well as the replacement policy. And we assume that randomization is used by default and implemented using a block cipher. Right. So we'll use two metrics to quantify our security results. So the first one being the eviction rate, which basically measures the probability or the rate of eviction the target address when using an eviction set. So a perfect eviction set, which basically means that it is algorithm independent, as in we do not consider a particular algorithm to create the eviction set, and we assume that the eviction set provided to us uh, was provided to us, and we use that to measure the probability or rate of evicting a target address using it. So this is a very popular metric used in previous designs, wherein you select a random target address X and you generate the eviction set E for that target address X, and you access the target address, you access the eviction set, and check whether the target address was evicted or not. And you do this in a loop, which will basically give you a rate or a probability number. The second metric actually quantifies security in terms of the number of LLC evictions needed to create a fixed size eviction set. So this is where the algorithm comes into the picture, and we test popular algorithms such as conflict testing and pipe and probe to quantify our security results. So the first knob is skewing. So we can have two subknobs under that, random skew selection as well as load away skew selection. So here we have two set of results. So we basically plot eviction rate against the eviction set size, and lower the eviction rate for a particular eviction set size, the better the security is. So we can see that as we go from a skew 2 design, which has random skew selection, to a skew 2 LA, which has load away skew selection, we see that the eviction rate actually drops quite a bit, and that means that the security improves. And we also observe that as we increase the number of skews from 2 to 16, the eviction rate drops by a lot. So we see that skewing helps improve security, and more the number of skews, the better it is. And load aware helps improve security on top of a random skew selection. But there are a few hidden nuances to consider here, which we'll come to at the end. Next up, we have extra invalid tags. So we can have two subknobs in that: the eviction strategy, which is where we actually evict the entry from, and the decoupling of the tag and data store, which was used in Mirage and Maya. So for decoupling, we observe that it has no security impact whatsoever on the cache design. For the eviction strategy, we can have two subknobs under that, and we can either evict locally from the set or we can evict globally from the entire cache. So here we have some results. So in this case, we use skews with load away skew selection and invalid tags, and we observe that invalid tags actually provide zero security benefit. Moving on, we have skews with invalid tags and global eviction, and we again see that invalid tags have no security benefit whatsoever. Finally, when we go to the configuration, we have where we have skews with load away skew selection, invalid tags, and global eviction. We finally start to see some benefit with invalid tags. So we can see that as we increase the number of invalid tags, our eviction rate drops drastically and improves security. So a bunch of configurations in this case for invalid tags do not actually seem to work, but only one specific combination works, which has skews with load away skew selection and invalid tags and global eviction. So we observe that extra invalid tags can indeed improve the security of the cache, but they need to be coupled with appropriate knobs and subknobs to do so. Right. Next up, we have high associativity. So typical caches usually have associativities of around 16. What we want to observe here is what happens if we take that all the way up to 128. So here we observe the sweep of associativity from 16 to 128. And we see that as we go up to 128, the eviction rate keeps dropping drastically, and uh, it provides us great security benefits. And moving on to the knobs of load aware with extra with invalid tags and global eviction, we again observe the same trend wherein increasing the associativity actually provides us great security benefits. And we can see that even with just two skews, we can have great security, which is even better than a large number of skews. Right. So next up, we have the replacement policy. So we'll consider four replacement policies here, random, and then three other deterministic policies. And RPLRU is basically a randomized pseudo LRU policy. It's basically designed specifically for randomized caches, and it's a more practical implementation of LRU as well. So talking about results here, so we see that all the deterministic policies actually seem to do better than a random replacement policy in terms of eviction rate. Even if we go to the knobs of invalid tags with global eviction, we see the same trend. What we also observe here is that GRP-LRU, or a global randomized pseudo LRU policy, actually performs similar to a global LRU. And we know that it is actually more practical to implement as well. So it's a very practical choice to use when one wants to use a global LRU policy, but does not want the impracticality that comes with it on a global scale. Right. So the final knob is remapping. So we basically define that in terms of the number of LLC evictions which we need before we have to remap. So we'll quantify that in terms of the algorithms to create the eviction set. So we have two algorithms, conflict testing and prime probe. And we see that conflict testing is much faster than prime probe, over 10 times faster. You can refer to the paper for detailed results on that. And when we talk about the number of LLC evictions, the higher the number of LLC evictions, the lower the remapping period, and therefore lower is the performance implication of that. So higher is better in this case. And we see that as we go from 2 skews to 16 skews, we see a great improvement in the LLC evictions. Similarly, as we go from just skews to skews with load away skew selection, invalid tags, and global eviction, we again see a great improvement. And finally, when we go to high associativity designs such as 64 and 128, we see large improvement in the number of LLC evictions. And if we were to couple this with invalid tags and load away and global eviction on top of the high associativity, we actually get a large improvement in number of LLC evictions on top of the regular skew design. Right. So let's talk about evaluating these knobs against occupancy-based attacks now. So here we basically look at the normalized number of encryptions needed to break these designs Uh, and we see that almost all the designs perform quite similar to each other, except for set-associative caches, which are slightly worse than the others. And we also talk about two partitioning-based designs here, which is SAS cache and way-based partitioning. So we see that SAS cache numbers are actually much larger than the others. And for way-based partitioning, we actually weren't even able to distinguish the keys at all. So it was completely secure against occupancy-based attacks. Now, if we were to talk about the replacement policy used, so we can see that a random policy is actually better than a deterministic policy such as LRU when it comes to occupancy-based attacks. Similarly, when we talk about the eviction policy, we see that Mirage uses a global eviction policy, and it does quite similar to the other designs which use local eviction policies. So there's no real trend to observe there. Right. So we'll circle back to the nuance we were talking about earlier. So we'll basically look at the impact of warm-up state now. So this was our original implementation for the eviction rate metric. And what we observe here is that the cache is initialized as empty, and it slowly starts to fill up with each iteration. So the cache rate never actually resets between iterations. And this will basically give us the effect of an average cache warm-up state for for the whole setup. But what we want to try now is, what if we reset the cache warm state at every stage and observe the effect of a particular warm-up state on the security of the cache? So why don't we use this technique by default? Because it's over 10 times slower than the original. So what we recommend is one uses the original metric to actually look at designs on a broader level. And once they've narrowed down to designs which are actually more secure than the others, they can use this metric to gain more information about how they perform under various warm states. Right. So here we basically talk about the design which has queues with load-aware queue selection. So warm-up is that design, but we set warm-up states for the cache at different levels. So we see that up till the 75% warm state, we actually have zero eviction rate in the cache. So the eviction sets are completely useless until that point. And when we go to higher warm states, such as 100 in this case, that is the cache is completely full at the start. We see that this result is actually exactly identical to the result with no load-aware skew selection and random skew selection instead. Uh, so we basically observe that the effect of load-aware actually diminishes as we go to really high warm states. Similarly, we do this with the addition of load-aware skew selection with invalid tags and global eviction as well. So we see a similar trend where going to a very high warm-up state will actually reduce your security benefit, and it'll actually bring you closer to the case where you don't have a load-aware skew selection. So we can see that cache warm state actually has a significant impact on the security of the design. Right. Finally, we also evaluate our designs, our various design trade-offs. So we've looked at security so far, which we've quantified in terms of the number of LLC evictions. We'll also look at the number of knobs used, which basically is a proxy for the design complexity of the cache. And then we have performance logic and power overrides for the designs. So we have quantified that for various designs that we've covered in the paper. You can refer to the paper for those detailed results. All right, thank you so much for listening. And our artifact received all three badges, and it also received the Distinguished Artifact Award. So if you want to take a look at our code base, you can scan this code or go to our website to look at that. And if you have any questions, feel free to reach out to us. Thank you.